In this video, we're going to cover sections 4.1 through 4.4. Chapter 4 is all about scatter plots. A scatter plot shows the relationship between two quantitative variables. And what we're looking for in particular is if there is a linear relationship or linear association between the points. So one thing that we want to look for when we're looking at a scatter plot is the direction. So you can think of direction as the slope of a line that would more or less follow the points. If the points are following a line that has a positive slope, then we say that the direction is positive. If the points are following a line that has a negative slope, then we say that the direction is negative. The second thing that we want to look at is form. And form is referring to whether the points follow a line, in which case we can say that it's a linear form. They follow a shape that is not a line. It could be something like a parabola or an exponential function. Or if they don't follow any shape at all and they're just kind of scattered around, then we say that there is no form. The third thing to look at is the strength of the relationship, and this refers to how well the points fit a line or another shape. If they fit a line very well and you can clearly see a line that would go through the points, then we say that the association is strong. If they fit a line kind of well, you can kind of see a line through the points, but the points are a little bit more scattered and not as close to a line, then we can say that it's moderate. And if the points don't fit a line very well, they're much more widely scattered and you can't clearly see a single line that all the points fall along, then we would say that it's weak. And we can also kind of go in between here, so we could say moderately strong or moderately weak if we felt that that was appropriate. And the final thing that we look at is we look for outliers. So an outlier is an unusual observation. We've talked about that before, but it's far away from the overall pattern of the scatter plot. So my overall pattern for this scatter plot would be a line sort of around there. My outlier is not anywhere close to that line. It's very far away from the line. So here's an example. We're going to describe this scatter plot. This is congestion costs versus freeway speed. So looking at this, I would say that the points fall pretty close to a line that has a negative slope, maybe somewhere around there. So I would say that the association is negative. Since they're close to a line and not another shape, it is linear. And then for strength, I would say maybe moderate or moderately strong. There's a little bit of an opinion when it comes to determining the strength of an association. And then lastly, are there any outliers? I don't really see any, so I would say no outliers. Section 4.2 is looking at the roles of variables in scatter plots. So we're going to position one variable on the x-axis and the second variable on the y-axis. And the way that we determine which one goes where is by thinking about which variable is the explanatory or the predictor variable and which variable is the response variable. The explanatory variable we could consider to be what's causing the effect to happen, and the response variable you can think about the effect. So the explanatory variable is causing what we see in the response variable. Explanatory variable goes on the x-axis and response variable goes on the y-axis. Another way to think about it is independent and dependent variables. The independent variable goes on the x-axis and the dependent variable, which depends on the independent variable, goes on the y-axis. So now we're going to talk about something called correlation, and we're going to come up here with a numerical value to measure how strong the association is. So we can use words like strong, moderate, but what we're going to talk about here is how to get a quantified value for how strong association is. And we're going to calculate a value called R, which is the correlation coefficient. Now, when we're calculating correlation coefficient, it's always between -1 and 1. It can be -1 and it can be +1. The sign tells us whether there's a positive slope or a negative slope. So R is positive for positive linear relationships and negative for negative linear relationships. We're only using R for linear relationships here. If R is +1, that means the points lie exactly on a straight line with a positive slope. If R is -1, the points lie exactly on a straight line with negative slope. The closer R is to 1, the closer the points are to falling on a straight line. So R being close to 1 means that the points are close to a positive linear correlation. R being close to -1 means that the points are close to a negative linear correlation. R values close to 0 imply no linear correlation, which is when the points are just scattered around. So here's some examples. We see this first one is a correlation of 0. The points are pretty widely scattered. Correlation of positive 0.5. The points are closer to following a line with a slope that is positive. You can kind of see a line like maybe around there. And correlation of 0.9, these points are much closer to fitting a line with a positive slope. Down here we have some negative correlations. -0.3, these are still pretty widely scattered, but they kind of make a line with a negative slope. R of -0.7 is much closer to a line with a negative slope, and R of -0.99 is pretty close to a line with a negative slope. The value of R has no units, and it treats x and y symmetrically, so if you were to switch the x and y variables, it would not affect the value of R. Correlation is sensitive to outliers. Outliers may cause more scatter to the pattern and they weaken the correlation. So if you have a lot of outliers, then they will cause your value of R to be closer to 0. So for example, we're matching each graph with the appropriate correlation coefficient. So 1 and -1, those are pretty easy to pick out because those are going to be exactly on a straight line. The 1 is exactly on a straight line with a positive slope. So that's right here. -1 exactly on a line with a negative slope. So that's right there. 0.88 is pretty close to a line that has a positive slope. There are two graphs where the line is has a positive slope and the points are kind of close. These two. Those two are going to be the values of the 0.88 and the 0.62. And the one that I would say is closer to a straight line is H. So I'm going to give this one 0.88 and I'm going to give this one 0.62. We have -0.91. That's going to be pretty close to a line with a negative slope. I think that looks like B. And not quite as close to a line with a negative slope is -0.71, and that looks like E. E is not as close to a straight line as B is. So that's going to be closer to 0 than the value for B. -0.21 and 0.05, those ones are a little bit harder to quantify. I would say that A probably is a little bit of a stronger correlation. It's not a linear relationship. So this part over here is going to cause the value of R to be closer to 0. But this part right here is, if you just look at these points, those are fairly close to a line. So I think that this is going to be the value. And then 0.05, I'm going to put that for D. You could argue differently for A and D and switch those numbers around. And you don't really know exactly what they are unless you calculate the value. So we'll just stick with that. D is pretty widely scattered, and so that's going to be close to 0. And the last thing to talk about in this video is lurking variables. And so it's important to remember that when we're talking about correlation, we can't conclude that a high correlation alone indicates that one variable is causing another. Oftentimes there's a third variable involved, which is called a lurking variable, that is affecting both of the variables at the same time. So, in this example, we have a scatter plot that shows life expectancy against number of TVs per person for 40 countries of the world. And so if you look at this, it does look like there's a pretty strong association. The number of TVs per person, it looks like more TVs per person equals a longer life expectancy. So does that mean that we should send more TVs to developing countries to increase life expectancy? No, having more TVs doesn't cause people to live longer. The lurking variable is higher standard of living. So people who have more TVs, or countries who have more TVs per person, also tend to have more money in general, and so they can afford better medical care, and they'll have an increased life expectancy because of that. So we say that the higher standard of living is a lurking variable. So buying TVs doesn't automatically cause you to live longer, but if you can afford more TVs and you live longer, that probably means that you have more money in general.